you need to get controls there? Okay. Okay. We're getting down to the wire. Okay, we have class this week, and then next week on Tuesday, I'm just going to review. I've created a sample exam for you that's online, and I think it became live for you last night at midnight or something like that. You probably want to wait until after we've talked about what we're going to talk about on Thursday before you work some of those problems. But again, that will give you some idea of the types of things you'll be asked on your exam. I went over to the testing center and wanted to have them hand out a scratch sheet, kind of like what I did for that last tutorial, so that you could carefully draw ray diagrams with your ruler and get a nice accurate ray diagram. It turns out that was one bridge too far for them. Because we have 550 students, they've got us down in the Richards building instead of the testing center, and they just don't have the facilities over there to be dealing with two separate handouts. And so they, it's not that they said no, it was more that they said, heck no. And so what I did is I took the problem that I wanted to put on that exam, and I just tacked it on to this week's tutorial homework. Okay, I really wanted you to have the experience of this problem, but you're not going to be able to do careful ray diagrams during the exam, and so I won't ask you to. In order to do that tutorial problem, I would like you to have some scratch paper that allows you to do careful ray diagrams. And so if everyone could take one of these, it'll help you. Who's my helper over here? Thank you. Okay. The other two classes, the one at 12:30 and 3:30, did not get as far as you got last Thursday. And so things, they just had a lot of questions, and so we didn't get through the polarization. And so we're gonna review that before we do special relativity today. Now, special relativity, I gotta tell you, there is some weirdness that goes on with relativity. We're gonna learn about some things today that you're gonna shake your head and say, no, Greg, that's not right. That's not right. And for me, I believe in relativity for much the same reasons that I believe in the gospel. And that is that I just keep on seeing evidences that confirm my testimony. It comes pouring in. And every now and again, I get a letter that's been sent out to all of my colleagues, and it's from someone somewhere in the world who's figured out that Einstein was wrong and that relativity is completely bogus, and they can prove it. Okay, and I take those letters and I put them in a file that I have that's titled Kooks with a capital K. Okay, and that's because you know, when you start attacking relativity, you got to give up some things, okay? For example, your GPS that knows where you're sitting right now, okay? Now, that GPS works by looking at a set of signals from satellites. And if I get a signal from a satellite and I know how long it took that signal to get from the satellite to my phone, well, then I know where I am relative to that satellite. I'm somewhere on the surface of a sphere. If I get a signal from a second satellite, and I know how long it took that signal to get to me, well, I know that I'm somewhere on a sphere relative to that satellite. And that's going to isolate where I am to a circle, which is the intersection of these two spheres. And if I know, if I get a signal from a third satellite, then that's going to isolate me down to a point. And then you get a fourth satellite and a fifth satellite, and it's just gravy. Okay. Now, if you calculate the distance or the radius of those circles without relativity, that GPS is going to get you where you want to go, as long as you're happy with being within 14 kilometers. Okay. That'll usually get you there, right? But if you take into account Einstein's theory of not only special relativity, but general relativity, and we do, your GPS does, then it can tell you which seat you're in. Okay, so in my mind, that little phone that you're looking at right now, instead of listening to the lecture, that's evidence to me that Einstein's theory of relativity is legit, there are other evidences that we'll talk about in today's lecture. Would someone be willing to open our lesson with a prayer today? Anyone? Thank you, sir.
Our dear Heavenly Father, we are grateful for today. We are thankful for our wonderful weekend we've had the chance to listen to prophets and apostles, church leaders to speak the words of the Spirit to us. We are grateful, Father, at this time as we're nearing the end of the semester that we'll have the chance to learn more these final couple of lessons. We pray at this time that our minds and our hearts may be humble, that we'll be able to learn the theory of relativity, and we'll be able to get all of our questions answered. Father, we love thee and we say this in the name of Jesus Christ. Amen.
Thank you. Okay. Oh, and a temple in Spanish Fork. It's gonna be like that meme that came out about Utah. They had the street sign that says next temple 0.2 miles. Okay, let's talk about polarization first. We talked about polarization as being the direction of the electric field in this oscillating E and M wave, electromagnetic wave, that travels through space at the speed of light. And we call the plane of polarization the plane that the electric field vector is oscillating in. Okay. Now, you know who that is. That's I Love Lucy, Lucille Ball. And back in the day, we would use antenna to get our TV signal, and you had to get it lined up with the polarization of the TV wave. Okay, we're going to talk about 4 different ways to polarize light. The first one is absorption, and what we do is we find a material that will allow the electric field to go through along one axis, but will absorb the energy along the other axes. And so we define an axis of polarization for that material, and that's that red arrow with the P on it. Okay, and so once light goes through that, it's going to all be lined up with the polarization axis. Now, in general, unpolarized light, which is just, you know, what you start with usually, when that goes through a polarizer, it lets half of the light through. Because I can always think of that light as being, you know, half along the axis and half perpendicular to the axis. And if it's randomly polarized, I can't imagine why there would be more than half on one of those axes. And so I get half of the light gets through. And so that's what comes through. That S vector, it's called the pointing vector. You're never going to need that on an exam, but that's just the flow of energy. The flow of energy. Now, if I put a second polarizer there, what I do is I take what I had, and what comes out is going to be some fraction of what I put in. And we had a formula for that. And so the 2 equations that we need for this absorption is the first one when we start with unpolarized light. And that's a very simple equation. Just half of it gets through, regardless of how I've oriented that first polarization. If I go through a second polarizer, in other words, if I already have polarized light and I send it through a second polarizer, now I get this cosine squared rule that will be on the front page of your exam. And so if I, as an example, if I start with unpolarized light with intensity of 58 watts per meter squared, and I pass it through a polarizer that's parallel with the y-axis, that's this first one here. The question is, what angle should I put in the cosine square rule if I have my second one rotated by 30 degrees relative to the first one? So we're going to use our clicker for the first time today. You're going to use it several times today. So keep it out. Okay, you can click now. And I believe your class got points for this last day, so you're getting double points. Double coupons. Okay. I think that's all of us. It's an easy question. Good. Okay. The answer, of course, is 30 degrees. And it doesn't matter whether you put plus or minus 30 degrees into that equation because you're squaring it's a cosine squared. Now, how much of the original light is transmitted through the second polarizer? Well, again, we got to use both of our rules. The light that goes through the first one is exactly half, because we were told that we were starting with unpolarized light. If we had an intensity of 58 watts per meter squared, we get half of that through. And then we take what came through the first one and we use that as the starting point for our cosine squared rule. we put the 29 watts per meter squared into the cosine squared rule, and we get 21.75 watts per meter squared. Okay, it's that simple. It's mostly just plug and chug. Now, if you have more than two, if you have three or more, it's always the angle from the last polarizer that goes in the cosine squared rule. And so if this is the polarization of the first filter, okay, there's the polarization axis, okay, and then this is the second filter. The angle that I want is the angle that goes from one direction to the other. And then if I go from this polarization axis to this one, well, now the angle that I want is from this angle to that angle, from 2 to 3. Okay. Now again, the polarization you saw last time, I'll just remind you. That, you know, once I put one of these on, I lose half of the intensity. But if I put another one on, if I do it perpendicular, I lose all of it, because the cosine of 90 degrees is 0. But if I do it at 45 degrees, some of the light gets through, okay? And the smaller I make that angle, the smaller cosine squared is, and so I get more light coming through. Okay. So without doing any fancy calculation, just using your reasoning, what if I start with unpolarized light, and then I put that light through a polarizer that has a polarization axis vertical, and then the second polarizer has its polarization axis 5 degrees rotated from vertical. The approximate intensity of the light that makes it through both polarizers is what percentage of what I started with. Okay, and so if, again, without using your calculator, just your common sense, which of those answers seems most likely? Okay, last call. Good. C is the correct answer. And that's because, you know, 5 degrees, that's not much, you know. The cosine of 5 degrees is going to be pretty close to 1. You know, that's going to let most of the light through that gets to it. But it started with only half the light, because only half the light made it through the first polarizer. And so just a little bit less than half is the correct answer. Now, the second way of polarizing light is something that you've experienced if you've gone water skiing. And that is that when you're out on the boat, it's really, really nice to have polarized sunglasses. And that's because the glare that comes off of the lake, when the sun is at certain angles, at a particular angle called the Brewster angle, is polarized. And even when it's not at the Brewster angle, but near the Brewster angle, the light is mostly polarized. And that Brewster angle is, if I come in at the Brewster angle, the light that reflects off of the water, in this case, I had glass, but usually when you're boating, you don't boat on glass unless you're really, really lucky and you get up early in the morning and that water's just like glass, okay? So the refracted ray that goes in and the reflected ray that comes off are at 90 degrees at the Brewster angle. And when it's at 90 degrees, the part of the light that is in the, we call this the plane of incidence, the plane that's described or defined by this incident ray and this reflected ray. And as I look at the light that comes in unpolarized, I can think of some of it as being parallel to that plane of incidence. And some of the light we call S-polarized, which is senkrecht. Those of you that went to Germany on your mission, what does senkrecht mean? Perpendicular, okay? So it's perpendicular to that plane of incidence. And it turns out that the parallel component ends up refracting, and none of it at the Brewster angle will reflect. And so what we get left is just the senkrecht polarization that is perpendicular. And we can define it different ways. It's perpendicular to the plane of incidence, but it's also parallel to the surface of the lake. Okay, and that's the way I think of it, is when it comes skipping off, sometimes the S polarization is kind of casually called the skipping off component, skipping off the water. Okay, that's what you get into your eyeball. Okay, now we can find that that Brewster angle just with what we know about Snell's law. If I have this interface between air and water, and this could be any slow medium, but typically we use water. If I come in at the Brewster angle, then the light is going to reflect off at the Brewster angle. And then it's going to refract or bend towards the normal, okay? And so the Brewster angle is such that these two rays, the reflected and the refracted, are 90 degrees from each other. And so I can say that that reflected or refracted ray is going to equal 90 minus the Brewster angle. Okay, how did I get that? Well, this dashed line represents 180 degrees. I've used up 90 degrees here, so that means that the Brewster angle plus the refracted angle have to be the other 90. Everyone see that? Okay. So now if I use Snell's law, the n in the first medium times the sine of that Brewster angle is going to equal the n in the second medium, that's water, times the sine of the refracted, the angle in the water. Well, that's going to be 90 degrees minus the Brewster angle. Well, you probably learned in your trig class that the sine of 90 degrees minus some angle is equal to the cosine of that angle. And you can test that out, okay? The sine of, say, 80 degrees is, let's say the sine of 10 degrees. Let's say 80 degrees is equal to the cosine of 10 degrees. And the sine of 70 degrees is equal to the cosine of 20 degrees, and so forth, okay? So I can write this as N1 sine of the Brewster angle is equal to N2 times the cosine of the Brewster angle. If I divide both sides by the cosine of the Brewster angle, I get the tangent of the Brewster angle is equal to N2 over N1. And that's going to give me the formula that will be on the front page of your exam. The Brewster angle is the inverse tangent of N2 over N1. So if you plug in the N2 is equal to water, 1.33, N for air is 1. If you plug that into the formula, 1.33, and take the inverse tangent, you get something around 50 degrees. That's the Brewster angle for air to water. Okie dokie doke. Let's move on. So I was wrong. It's 53 degrees. My bad. But there's the formula for the Brewster angle. Now, so that's the skip part of the wave. So the question is, when I buy those polarized glasses, to get rid of this glare that comes off of the water on the lake or the water on the road if you're driving on a rainy day, how would you like that polarization axis on your glasses to be oriented? Okay. Do you want the polarization axis to be vertical, horizontal, or at an angle to the vertical? Or I just don't know. So let's use our clicker again. Again, the whole point is to block the glare that's skipping off the water. Okay, I think that's all of us. Okay, correct answer is vertical. Again, we want to cut out that glare which comes off the water parallel to the water or horizontal. And so we would like our polarization axis to be vertical. Okay, refraction can sometimes polarize light. If I have certain materials like calcite, we find that it has a different index of refraction for the different polarizations. And so that means that the light bends at different angles depending on whether the light is polarized one way or the other. I have an example of that here. You see, I've got this little red angle sign there. and a piece of calcite. And you see that if I turn it in certain ways, I can get essentially the light to bend in two different paths. And so where I originally just had one angle sign in red, now by the time it gets through the calcite, it's bent in two different directions, and it appears like there are two there. And what I would find is that the light from one of those is polarized one way, and the light from the other one is polarized the other way. See how it changes from one to the other as I turn my polarizer? It's magic, pretty much magic. Allura Mora. Okay. Now, that's not going to be on the exam, okay? So just, that was for just interest, okay? But essentially, we say that that material is birefringent, and it has two different ends depending on the polarization. Now, the last way, which is also not going to be on the exam, is that when light gets scattered, for example, when light comes from the sun, it's white light. But when I see the sun, it appears yellow. And the reason for that is that, remember, white light is red, green, and blue. And what happens is that the blue light is right at the right frequency to be absorbed by elements in the atmosphere and then re-radiated in all directions. The sun is sending light straight to us, but the blue light is getting scattered in all different directions. And because of that, the light that comes from the sun is missing that blue light, because that got scattered all over. That's why the sky looks blue. And what happens to white light when you take away the blue? You get red and green. And red and green light gives you yellow. Okay, remember back to our color discussion? Okay, well, it turns out that that scattered light that's sent out in all directions gets polarized along directions that are perpendicular to the direction the light came in at, for reasons that we're not ready to talk about. But as a result, if we have these polarized glasses, we can sometimes cut out some of the light that's being scattered from the sky. And so you see on the right, I've got a polarizer, and on the left, I don't. And you see we've cut out some of the light with our polarized axis. Again, that's not going to be on the exam. Let's talk about relativity. How many of you have studied relativity in some way before, a class or just on your own? Raise your hand. Okay, those would be the geeks in the room. I love you. Okay, good. Einstein, I marvel at his brilliance and also the simplicity when you think of it, of his ideas. He argued two postulates, and based on those two postulates, he just changed the world of science, just on those two postulates. The first postulate is called the relativity postulate, and that's how the whole thing got its name. And it just says that the laws of physics should be the same for any inertial reference frame. Tell your neighbor what that means, inertial reference frame. What's an inertial reference frame? Tell your neighbor.
It's like a mirror, you're strapped and let's walk out and reach the side. There's both different frames.
Okay. In- In physics 105, we talked about an inertial reference frame as one in which Newton's second law applied. Okay? If you're on an airplane and you put down the food tray while you're sitting on the runway and you put a marble on that tray, it stays there. Okay? Things at rest stay at rest, things in motion stay in motion. If you're flying at 600 miles an hour, but it's a constant 500 or 600 miles an hour, and you put the tray down and you put the marble on the tray, it stays there. Exactly the same as when you're on the runway. But when you're taking off, first of all, they don't want your tray down during that time, but if you did put your tray down and put a marble there, it doesn't stay put, okay? So an inertial frame is one that is not accelerating. And I misspoke before, it's Newton's first law that is valid in a inertial reference frame. And that tells us when we can use Newton's second law, okay? So no one frame is preferred over any other as long as they're both inertial reference frames. This seems reasonable, okay? We hope that aliens in other galaxies have the same laws of physics that we do, okay? Now, the second postulate is where things get weird. He argued from purely mathematical reasoning, from Maxwell's equations and what we know about wave mechanics, places that we're just not ready to go, but which I do go with the engineers that have calculus. He argued that the speed of light has to have the same value, that 3 times 10 to the 8th meters per second, in all directions and in all reference frames. And sure enough, we've done test after test after test of this, and it turns out to be right. It turns out to be right, okay? Now, that's weird. And it's just contrary to our everyday experience. What that means is that if I'm in a plane and I throw a ball, relative to the Earth, the speed of that ball is the speed of the plane plus the speed of the ball. Okay, I have to add those together. Likewise, if I have a sound wave propagating from the back of the plane to the front of the plane, and it has to propagate through air, it needs a medium to wiggle, to wave. And what we find is that relative to the Earth, I have to take the speed of the plane and add it to the speed of the sound to get the total speed. But light doesn't wiggle anything. It travels through vacuum. Essentially, it just wiggles itself. The changing electric field changes the B field, which changes the electric field, which changes the B field. It doesn't need a medium. And what we find is that whether we measure that speed in the plane or from the Earth, we get the same value. I mean, think of that. You've got a car coming towards you at 9/10 the speed of light. It turns on its headlights, coming towards you. You measure the light coming towards you from a car going 9/10 the speed of light. And what you measure is the speed of light. Okay? Yeah, okay. Jameson's shaking his head. So that's weird. That's weird. Live with it. Okay? Okay, it gets weirder. There are 3 effects from this weirdness. The first one we call time dilation. The second one we call length contraction. And the third one we call relativity of simultaneity. So let's take them one at a time. I can make a clock using a light source like a laser. And I just, put a detector on the bottom, I put a detector on the top, and I've got mirrors on top and bottom. And as this light bounces back and forth. Every time it hits a mirror, it goes tick, 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 tick. Okay? Now, if I measure the time between ticks, I think we can agree that that's just going to be the height of that container divided by the speed at which the light is moving. Okay? Now, if I take that height to be 30 centimeters and the speed of light to be 3 times 10 to the 8th meters, when I use that formula for delta t, I get 1 times 10 to the minus 9 seconds, or 1 nanosecond. 1 nanosecond is pretty quick. Okay, but that's the time that we measure if we're in that container, essentially with the clock. However, if that clock is moving relative to the sidewalk, an observer on the sidewalk is going to see something different. Okay? In the time it takes for the light to go from the floor to the ceiling, we'll call that time delta t prime. Remember, before we had delta t 0, which we sometimes call the proper time. But the time that it takes for this light to get from here to here, as observed by someone on the sidewalk, is now going to be this distance divided by the speed of light. And this distance is a longer distance than that distance. Okay? Well, let's see how much longer. We can use Pythagorean theorem. The hypotenuse squared is just this side squared plus this side squared. This is how far it travels in the time that the light took to get from here to there. Is everyone still with me? Okay, now we're going to do a little bit of algebra, not a lot. Remember, h I could write as just the speed of light times the proper time. That's the time it was measured by someone inside the container. Okay. And so I can plug that in for h. And then I can use this equation for d. D is going to be the speed of light times this time that it took to go from here to here, what we're calling delta t prime. If I plug that in for d and I square both sides, I get this equation. And you can go back and read this, or you already did when you prepared for class today. Now, if I put all the red delta t primes on one side of the equation and all the blue delta t zeros on the left side of the equation, I get this. And then I can write this. Now, this factor here, square root of 1 over b over c squared, we're going to give a name to. We're going to call it the relativity factor. Okay, we're going to call it RF. And that's equal to square root of 1 minus b over c squared. And that we're going to use over and over and over again. Over and over and over again. Now, let's wrap our head around what this means. The time between ticks is going to seem shorter for someone that's moving with the cart. But someone looking from the sidewalk is going to say, oh, I saw that as taking longer. I saw that as taking longer. So if I look at this equation that we just derived, and then we look at how much longer it looks to someone on the sidewalk, I just divide both sides by that relativity factor. Because that relativity factor is always less than 1, I'm going to get a number bigger than 1. So if you're in that container with the clock, okay, if the clock's not moving relative to you, you think the time between ticks is only 1 nanosecond. But someone looking inside from the sidewalk says, oh no, the time between ticks was longer than 1 nanosecond. So someone on the sidewalk is going to say, hey, your clock's running slow. Okay. According to my watch on the sidewalk, your moving clock is running slow. And so that's the first weirdness that comes out of relativity. The moving clock runs slow. Now, again, we have evidence. In the 70s, we put cesium clocks, atomic clocks, on 3 different airplanes, and we raced them around the world at high speed. And we found that the clocks that were moving, when they came back, were behind the clocks that stayed in the lab by an amount that was predicted by Einstein. Okay. Again, this is what we have to take into account to make your GPS work. Those satellites are moving. That's going to introduce one of these time delays. Einstein's general theory of relativity also says that that the strength of the gravity that the clock is in is going to affect whether it runs fast or slow. And that turns out to be also an important effect for your GPS. So let's look at this relativity factor. In order to make some of the problems kind of more intuitive and less math-like, we look at some values of V over C where the numbers turn out easy. If your speed relative to light is 3/5 or 60%, then the relativity factor is 80% or 0.8. If your speed is 4/5 the speed of light or 80% of the speed of light, the relativity factor gives you 60% or 0.6. If you're going 95% of the speed of light, it gives you 0.3. And if you're going 0.995 times the speed of light, it gives you 0.1. And so these are numbers that are just handy, when you're working problems. In my textbook, these are the numbers that we tend to use in our examples, okay? Now, the second weirdness that comes from relativity is length contraction. And this comes from that first postulate of the relativity postulate, and that says that there is no preferred frame of reference. Or maybe a better way of saying it is that all frames of reference are preferred, equally preferred. We're all special, okay? Okay, that's what we learned at conference, if you'll remember, okay? Now, that means that if I have one car moving relative to another, observer A moving and observer B parked, it's no different than if observer A was parked and observer B is moving at constant velocity. It has to be an inertial reference frame. And that means that anything that I can determine about that other observer, the length of their car, their speed, their mass, they must have determined the same thing about me. Otherwise, that relativity postulate just is no longer true. Okay? Now, what does that mean? Well, suppose I have this cart and it has a clock on it and it is traveling at 4/5 the speed of light. if you'll believe it, 80% of the speed of light. Well, what that tells me is that if we measure the time it takes for that moving clock to move from the starting flag to the finish flag, with the distance between them being 240 meters, as measured by us on the sidewalk, okay? We would say that it should take that cart, I just take the distance it travels, 240, divided by the speed, 4/5 the speed of light, and I get 1 microsecond. I say it should take 1 microsecond to get through from flag to flag. Now, for 80% of the speed of light, 4/5 the speed of light, the relativity factor is 60% or 0.6. So we would say that that moving clock runs slow. So whereas we measure that it takes 1 microsecond to get from flag to flag, we look at their clock and we say, hey, it's not going to take as many seconds. That relativity factor is going to make sure that their clock runs slow. So if my clock is reading 1 microsecond, their clock is only going to read 60% of that, or 0.6 microseconds, okay? And so that brings up a problem. If in their moving frame, their clock only moves 60% of a microsecond, how are they going to measure the same speed? How are they going to agree that one is moving at 4/5 the speed of light relative to the other? Well, the only way we can do that is if the distance between the flags gets contracted in that moving reference frame by the same relativistic factor. So in the moving frame on the cart, it seems like only 0.6 microseconds passed, but it also seems like the flags were only 60% of 240 meters or 144 meters apart. So someone that's on that cart is still going to measure, oh, the flags are coming at me at 4/5 the speed of light. Okay, 4/5 the speed of light. See if your neighbor is on the bus. This is a weirdness. This is a weirdness.
Watching the bus go by and relative to the light, it is a thought person. You saying that like, oh yeah, small company can understand that. Yeah. But it's how we're saying that, like we're saying that. Like the math, like I'm gonna be divided by.
Okay. Now, let's practice this. We see the USS Enterprise fly past our home planet at 60% the speed of light, 3/5 the speed of light, and we measure its length to be 236 meters. What length would Scotty measure as a crew member on the ship? Okay, well, it turns out that the longest length, when you're deciding whether I use that relativity factor to make something bigger or making something smaller, the longest length is going to be in the frame of reference where you can take your sweet time making the measurement, where you can take your measuring tape and go from one end of the Enterprise, you know, just 20 meters at a time, and just take your sweet time measuring the length of that ship. That's going to be the longest length. If, however, you're measuring that ship as it goes zipping past your planet by just, having different people at different places now, and you've got to take those measurements right at the same time here and there. That's going to be the shorter length that's going to be shorter by this relativistic factor. Okay. In this case, the relativistic factor is going to be 80% or 0.8. And so the question is, if I want to know the length that Scotty measures, do I want something bigger than 236 or smaller than 236? Bigger, because Scotty's on the ship. He can take his sweet time making that measurement, okay? And so I would divide by the relativity factor to make that 236 into 295, okay? Does that make sense? That's the easy, in my opinion, that's the best way to think of these relativity problems. To always think of the time is always going to be shortest in the frame that's moving with the clock, okay? And the distance is always going to be longest in the frame that's moving with the meter stick, okay? Where you can take your sweet time to make the measurement. Now, let's do our clicker again. A spaceship is 100 meters long when it launches. Eventually, it gets up to 95% of the speed of light. How long is the ship as measured by someone who remained behind on Earth? And remember that the relativity factor for 0.95, the speed of light, is 0.3. So with your clicker, now you can click.
Well, someone can remain.
Okay. We're almost there. Think that's all of it. Good, the answer is 30 meters. Okay. In this case, we want to get a smaller number than 100, and so we multiply by that relativity factor. And since the relativity factor is 0.3, 100 meters times 0.3 gives me my 30 meters. On the other hand, and everyone should get this one right, what if it gets up to 95% of the speed of light? How long is the ship is measured by someone on the ship? On the ship. So clicker question again. Okay. This should be one that we all get right, so that we all go to Disney World. Okay. We're not going to Disney World, but the answer is 100 meters. Okay. Oops. Oh. Okay, now, what's the evidence of this contraction? The evidence came first in 1962 from a research group at MIT. And they did a study with Mount Washington, and they had a detector that detected muons at the top of the mountain and one at the base of the mountain. And these muons were coming very, very fast from interactions in the atmosphere from solar wind. Okay, and the speed of those muons was measured to be 0.995 times the speed of light. Now, you remember that the relativity factor for .995 was 0.1. Now, the half-life, which we will talk about on Thursday in detail, but you've lived long enough to know what a half-life is. You know, things that are radioactive, they have a half-life. And that means that just like popcorn, there's a probability that any moment one of them is gonna decay, you know? And the half-life tells you what that probability is. After a half-life, you would expect half of the particles that you started with to have already turned into something else. If you had 100 muons, after 1.5 microseconds, you'd expect only 50 of those. And after 2 half-lives, you'd expect only a fourth of those, 25, and so forth. Well, the time that it takes that muon at this speed to get from A to B is 6 microseconds, which is 4 half-lives. And that means that, you know, I should only have 1/16 of the particles that I started with. If I measure how many muons I detected each second at A, I should get a number that's 1/16 when they get to B. If I discount relativity, if Einstein was just a kook, okay? But what we measure is at B, I get something bigger than a half. It's not 1/16, it's bigger than a half. And that's because I can think of a clock in different ways. A clock can be something that you put on your arm, or there's biological clocks. My heartbeat, okay, is a clock. And my aging can be thought of as a biological clock. And so if I'm moving very quickly, my aging process is slowed, just like any other clock would be slowed going approximately the speed of light, okay? And so what that means is that the moving clock, namely the lifetime of those muons, has to be multiplied by this relativity factor. And so that means that the time according to the muon that it takes to get from point A to point B in their frame of reference is just going to be 1/10 of 6 microseconds or 0.6 microseconds, which is less than 1 half-life. And that explains why I still have more than half of them left, because they don't think that time progressed as quickly as we do, okay, in our lab frame. Well, how does that work with the relativity postulate? There's no preferred inertial frame, so I should get the same result in the muon rest frame. Well, in the muon rest frame, they think their half-life is 1.5 microseconds. In their frame, they're not moving. Their clock's not running slow. You know, I probably have 1.5 microseconds to live here, guys. You know, how far am I going to get? So how do we get the same result, whether we're looking in the muon frame or whether we're looking in the lab frame at MIT? Well, this is the Earth reference frame, but in the moving frame, in the moving frame, we have that length contraction. The muon clock is running slow in the Earth frame, and that's how we explain the discrepancy in our data. But in the moving frame, the muon doesn't think he's moving, but he sees Mount Washington and MIT's campus coming towards him at 0.995 the speed of light. Okay, and that means that the distances, Mount Washington looks 1/10 as tall. If you can imagine, the Great Dome at MIT is 1/10 as tall, which is going to make it a whole lot easier for those freshmen to put that police car on top of the Great Dome. They always do that, usually at night. Okay, and so either way, we have more than half of those muons surviving. In the Earth reference frame, because their clock was running slow, in the muon frame is because I really didn't go very far. See if your neighbor followed that reasoning. Now, there's one last weirdness, relativity of simultaneity, and this is the weirdest of them all. And this is the one that accounts for all of the paradoxes that you find attached to relativity. The twin paradox, the can I get that hole in the barn paradox. This relativity of simultaneity says that if two events are simultaneous, namely happen at the same time in one reference frame, and they're separated by some distance in that frame, then they cannot be simultaneous in another frame that's moving relative to the first frame. Now, let me see if I can justify that. If we look in a moving frame, say a train car that's moving at some appreciable fraction of the speed of light, and we want to synchronize our watches, our clocks, and one is at the front of the train and one's at the back of the train. Well, in the frame reference of the moving train, those clocks are not moving. If I'm in the train with the clocks, they're not moving. And so I can synchronize them by flashing a light in the middle of the train. And when that light reaches my clocks, they turn on. They were set at 0. When they get that flash, they both turn on. And that means they're always going to read the same value. Okay? Now, if I look from the sidewalk frame, the speed of light has to be the same for both frames of reference. And so in the sidewalk frame, I see that bulb flash sending light at the speed of light both towards the front of the train and the back of the train. But because the back of the train is coming towards the light and the front of the train is going away from the light, that pulse, that flash that's going to start my clock is going to hit the trailing clock, the one at the back of the train first. And it's going to start reading time. It's going to start ticking before the one at the front. And so we say that trailing clocks always lead. What that means is that when this leading clock finally turns on, the trailing clock has already been on for a while. If this one reads 0 afternoon, this one reads something bigger than 0 afternoon. And that causes a lot of confusion. Now, I'm going to give you a formula that you're going to need for your homework. And that is that if two clocks moving with velocity v relative to us on the sidewalk are separated by a length L prime as measured in their own reference frame, okay, so that would be the proper length, the maximum length, then as seen by us, the reading on the trailing clock will always be ahead of the clock that it is chasing by a delta t prime given by the proper length, the speed of the train divided by the speed of light squared. Now, in our book, we go through a very careful derivation of that formula. And I'm not going to drag you through that right now. And the reason I'm not going to drag you through that is because we have the unforum today. Everyone know what the unforum is? There's going to be all sorts of dancing, entertainment. I think there's going to be explosions, all sorts of fun. And it is not televised. So you need to move your young selves over to the Marriott Center to participate in that. So we'll pick this up on Thursday. We still have a little ways to go. Yeah.